Can everyone see that all well?
Yep, looks good.
All right, perfect. All right, yeah. So, hi everyone. Thank you very much for having me. My name is Land-Strykowski. I'm a PhD student just finishing off my first year at the University of Sydney Institute for Astronomy. I work with Grant Lewis and Tara Murphy on a cosmological tension problem, which is one you may have heard of, or you may have not. By the end of this little update, you'll have an idea about this particular problem and why I think it's interesting. So it does relate to the cosmological principle, which is this assumption in cosmology that the universe is the same everywhere and the same in all directions at a sufficiently large spatial scale. This statistical assumption is really important. It underpins a lot of modern cosmology. We use it to generalize things that are far away from us, or at least theories about them. It underpins the Freeman-Lemaitre-Robertson-Walker metric of space-time as part of the standard concordance model of cosmology, lambda CDM, called dark matter. So it is really important. This old, essentially, assumption has been built on over time to give us our modern view of the universe. So because everything rests on the symmetry assumed in the cosmological principle, it's important to constantly come back to it and reinterrogate it. And by doing that, you also want to reinterrogate the evidence that supports it. And one of the biggest pieces of evidence for the cosmological principle is the cosmic microwave background, the radiation from the very early universe that looks pretty much the same temperature everywhere. These small temperature fluctuations that we're seeing here of order delta T on T 10 to negative 5. So the CMB is pretty much this uh, smooth map from the early universe where it was smaller and came into thermal contact and came to thermal equilibrium. And the idea is that this structure that we see on the CMB would then have grown via gravitational instability to give us the large scale structure in the universe today. So by this being smooth, we then feel confident that the larger universe today should also be smooth. But this isn't actually how the CMB looks like. This is the real CMB. It is not smooth in the same temperature everywhere. It has a big temperature dipole. When one direction of the sky, the temperature is much larger than the mean, and the other direction of the sky, the temperature is lower than the mean. And this is typically removed because it's attributed to being a systematic effect from our motion along that line of sight, causing a Doppler boost in our observations of the CMB because we're not co-moving observers. If you run the machinery and you work out what velocity is, it turns out to be towards that location in galactic coordinates at around 370 kilometers per second. And by motion here, I mean our peculiar velocity, which is the velocity of our solar system around the galaxy and the velocity of our galaxy around the local group. And these are combined together. Then this is all fine. But the problem comes that if this imprint, this dipole, is caused by our motion, then we should see this same imprint when we look at other objects in the universe. We should be able to interrogate whether this interpretation is correct for the CMB and whether the CMB is isotropic and homogeneous by looking at other types of objects in the universe, like radio sources and infrared selected quasars. So when you're looking at these large surveys of cosmologically distant objects, your velocity is going to do two things. The first one is relativistic aberration. If you're not moving, you see an object at a certain angle towards you. If you start moving, that object will appear to aberrate and move in the direction of motion, becoming closer to where you're moving to. And this angle will go down. When it comes to looking at lots of objects all together in the sky, the effect is a little bit different. Here, I've divided the sky into equal area pixels. The different colors of the pixels don't matter, it's just showing you that they're different. And rather than putting dots in every pixel, I'm just focusing on those 9 ones in the middle. And I've put 4 dots representing 4 sources in every pixel to represent that, that the sky is the same everywhere and it's homogeneous and nice. And this is assuming that the cosmological principle holds, and it's also assuming that we're not moving. Now, we're going to pretend we are moving. Let's imagine we're moving towards that center pixel on the sky. By relativistic aberration, moving towards that center pixel will cause these sources to aberrate in and cluster and move closer together. What this means is if you're measuring the density per pixel on the sky, then the density is going to increase in the direction of motion, and the density is going to decrease in the anti-direction where you're coming from. So you can measure this in the sky and infer your motion. Another thing your motion does is a Doppler shift. In your flux density limited survey, when you're only including objects above some critical flux density limit that you've imposed, which is standard practice, what will happen is in the direction of motion, where the apparent flux density of objects is being boosted up because of the Doppler shift, those sources that shouldn't have been included intrinsically will be boosted in. And then you also have deboosting, where sources are being boosted out of your survey in the opposite direction. So what this means is you're going to be able to detect and count more in front of you and detect and count more less where you're coming from. So both these effects work in harmony and were first proposed in 1984 by Ellis and Baldwin, well before we had the ability to actually test the cosmological principle with these sources. Now, just to recap how this relates to cosmology, is we can take a survey of objects that I've mentioned, and you can measure the dipole, and you can measure the density fluctuations. And this dipole agrees to the CMB, we're fine, and we go home. If it disagrees, that indicates that there's something going wrong that we don't understand. This could mean that there's something wrong with the distribution of these sources, that they're not isotropic and homogeneous. The universe might have some, you know, desired direction to distribute these sources. And anything like that, any anisotropy would violate the cosmological principle and bring a lot of the modern cosmological view tumbling to the ground. So that's how we can do these tests using these data sets. So in the literature, people have done this test with various data sets and found that the dipole direction you infer pretty much agrees to the CMB. Here we have the CMB star, and it is in 2 sigma agreements with MVSS and RACS, which are prominent radio surveys, which I'm sure you know, and I'll cover these a little bit in depth later. But we have directional agreement. But the amplitude consistently diverges from the expectation. Here, we'd like it to fall at the gray line of 1, which is the CMB amplitude, and we find that across radio, infrared, and optical continuums, that it is consistently at 2 to 3 times. So if you're just taking this as a kinematic effect, we're not moving at 370 kilometers per second. This is implying that we're moving at 700, 800, or 900, which is in clear disagreement and tension and implies that there's something else going on other than kinematic origins, which we don't know what it is, and that's the anomaly. So this problem has gotten worse and worse over time. It is concerning now. Ever since it was first theorized in 1984, things have gotten worse. And when MVSS was first published, people did the test and found that there was not much wrong. They found agreements. And then with larger data sets, the agreements has really diminished over time, especially with RACS and the WISE catalog of infrared selected quasars. The challenge is now strong. It is in disagreement with the CMB at over 5 sigma, and this seriously poses a significant challenge to the cosmological principle and the standard model of cosmology. And this significance of tension is now beyond that of the Hubble tension. We're not talking about, the difference between, 67 and 68. Apologies if the numbers are wrong there. We're not talking about those small numbers. We're talking about 300 kilometers per second to 800 and clear disagreement, even with large error bars. And last year, there was actually a meeting run by the Royal Astronomical Society, so in the UK, which is a cosmology meeting just focused on cosmological tensions. And the conclusions of that meeting, I didn't go, my supervisor did, but the conclusions were that this dipole problem is the current focus. The other tensions are important, but this is a way forward, and it seems concerning. You can see of recent citations that this is a focus as well. So what are we doing about it? Well, the literature and us as well have looked at key radio surveys, MVSS at 1.4 gigahertz and RACS-Low-1 887.5 megahertz. The masking that you see here is to mask out the galactic plane, where we have spurious sources, and also the mask accounts for the declination limits of these surveys being in the northern southern hemisphere. We also look at CatWise, the infrared selected quasars. Here to make sure, to attempt to make sure that they're quasars, you take particular color cuts, and this is observed in the W1 and W2 bands. And we also look at Planck, again, which is the CMB. And what we do is we run our machinery, which I can answer more questions about later if you'd like, to essentially infer what dipole and what velocity we should get from these surveys. And the 3 ones that are not the CMB are smoothed, so we can see what's going on. And you can instantly see that we have a problem. Rather than the nice dipole of the CMB, we have very different structure. If you kind of blur your eyes, you can see CatWise there's a dipole, but you have higher order quadrupole there. MVSS, you can kind of see the dipole, but there's all this other structure. And RACS, well, this looks very different as well. So you can see this disagreement. And to quantify this, what I have particularly focused on is using cutting-edge Bayesian techniques to assess the tension between the surveys. Here, the sigmas between these are the tension. And the sigma here is essentially the probability of observing these data sets being this discrepant by chance, assuming that they should have been concordant to start with. So what we find is that between CatWise and MVSS, very different surveys done 20 years apart. CatWise and MVSS have completely different systematics. CatWise was satellite-based, MVSS ground-based, and they're in really low tension, 0.5 sigma, which is quite a lot of agreements. This is telling us that there's likely a common signal, a common physical phenomena behind what's going on. And when you look at CatWise comparing to Planck, you find over 5 sigma tension. This corroborates recent results in literature that have also looked at catwise, and we've used a new Bayesian technique to quantify that here, and it corroborates. So this strengthens that challenge against the standard model, and there is a problem. Now, looking at racks, this is a bit of a different story. We're seeing that it is in moderate tension with pretty much everything else at the 2 to 3 sigma level. And this is telling us that we need to look a bit more into what's maybe happening with the racks data. Maybe there's something there that we're not quite understanding, because why is it in moderate tension with everything else? So that is a point of further investigation. This dipole effect that we're measuring across the sky, based on what we think our velocity is, around 370 kilometers per second, it's a really small effect. We're looking at a modulation of about 0.1% across the sky. So it's sensitive to noise, it's sensitive to so many things, including ionospheric temperature fluctuations and the flux scaling that you do. Here we have 3 different maps of Rack's law where they've been treated slightly differently during the catalog creation process. And these differences based on observation frequency, but also based on the flux scaling, you can see it causes very different structure. Again, this is smooth just so we can have a look at it, but qualitatively, you can see that you get very different dipoles here. And we find that when we run the models for it. And also your choice of resolution convolution significantly can affect the dipole just because it's so sensitive. So we really have to understand what's going on here. And looking into the future, we're going to have to be able to quantify, model, and understand the nuances of not just racks, but every single data set, because we're getting to the point where we have lots of sources to use. So now we need to use the sources appropriately to get a reliable measurement. And this also relates to other forecasting that we're doing. The Sydney dipole group that I'm part of, as part of the dipole chapter for the SKS science book, we're working on mock skies, predictions of what we think we will observe with the SKA. And again, to reiterate, we need to go beyond just a high number counts because we're essentially there. We have the information now. We need to look at sensitivity masking and the effect of other things inside the surveys and really understand what is going on to get a realistic measure. So we're building big pipelines to essentially calculate and input dipoles on mock SKA skies at different Briggs configurations and with different masks and everything. And this is very exciting at the moment. But also, rather than look at things that are a bit more to the future, SKA will take a while to come, EMU is here. And whilst it's not finished yet, when it is finished, we're going to get, well, it anticipated to get around 7 times 10 to the 7 sources, which is very exciting, and we can do a lot of inference with that. But even currently, with the patches that we have, we can make very good inference. This might be a bit counterintuitive. A lot of people that are not in the dipole field think that you need high sky coverage to get good inference. And you actually don't. You can have small patches of sky and get really good inference of what the dipole properties are. This recent paper by my colleague looked at that as part of it. This is a patch of sky, and they only use that, and they move this around the sky at different pixels. And in each of these big pixels, this is the inference you get. Where it's more yellow, you have more support. You have a higher base factor, which is support for there being a dipole rather than there just being a monopole. And when you're near the poles, so this is the dipole direction, the anti-direction based on the CMB direction. When you're around the poles, it looks homogeneous and the same, so you don't make good inference. But when you get to the equatorial region of the dipole modulation, you can get really good inference. And what you just care about is the total number of sources. So it is a high priority to get these pipelines working with EMU straight away because we have the means to do it, and we're likely to make some very interesting inference. But again, we need to get round to it because we have a lot of projects going on simultaneously. But it is a high priority. Now, I've talked a lot about information levels, and there's not much longer left to talk. This is the last bit here. I did simulations myself to try to see how our inference is going to change at different levels of information. I did a lot more variance from 50 to 5 million sources in this, but I've chosen the 3 most important cuts. Now, by simulations, I mean I take a sky that is homogeneous, and then I modulate it with some dipole and take a Poisson draw. And I do this for the dipole inferred from MBSS and RACS, the radio continuum. And I also do this for the known CMB dipole. And I compare these simulations to the Planck data itself. So if you're comparing the CMB dipole to the Planck data, that should agree. That's our concordant control set, the blue one. Whereas the radio continuum dipole should disagree with the Planck dipole, and that should get more prominent as you go to more levels of information and your posteriors get tighter. And that's what we're seeing here. At low sources, when you have no information, the posteriors of both the red and the blue simulations are so wide, they look the same. And you can't tell which is which. You have the you have shot noise dominating. So here you have this degeneracy. If you were to look at these data sets and get attention around here, you can't tell where it came from. Whereas In the current realm of the amount of sources we have, around 500,000 the radio surveys, if you have a result around here, you can tell it's tension. A result around here, you can tell it's concordance. But our results are around here in this degenerate region. So we've got unclear inference. And looking into the future, we want to be in the right-hand panel where we have many more sources, and these two distributions are very far away. So if you get any inference around here, around 3 sigma or less, or in the upper red area, you know very clearly that you have a common signal or you have tension. And that's what we're looking towards for the future. So just to wrap it up, the cosmic dipole tension is a significant problem in modern cosmology, and it is an unsolved anomaly. And it does pose a significant challenge to what we believe in the universe. And the measurements here, we need to understand what is going on with the survey specifically to get reliable measurements going forward. And with RACS, SK, and EMU, we'll be able to work out whether the radio continuum also poses a challenge to the cosmological principle, which the current challenge is with the infrared selected quasars. Thank you.
Oh, that was really interesting. I haven't heard about that for a while, so it's good to get an update. We've already got some hands raised. Larry.
So that was one of the best cosmology talks that I have heard in a very long time. So you should feel really good that you're starting off your career that way.
Thank you, Larry.
Can you give us an idea of the relative size of the density change relative to the size of the number counts changing because of the color correction, boosting in and up, in and off, out of the threshold?
Okay. Um, I'm just going to try and make sure I understand your question completely. So the question is, uh, how does the total number of sources that we're working with in a given survey and math that we've used compare to the actual modulation we're getting across from like the most significant areas of the poles? Is that your question?
No, you
Ah,
started the talk by talking about two different effects.
yeah.
One is a geometric effect, and one is a spectral effect.
Oh, okay, yeah. So is your question
Yeah,
regarding what's the like kind of proportion of each of those?
yes,
Which one?
yes.
Uh, so I must say I don't actually know the proportion of them. I've essentially used the Ellison-Baldwin formula and test, and also understand its derivation. I've only ever used them like in uh in harmony together, and I don't actually know yet the proportions of how much each of them are. That'll be interesting to check out. Yeah,
Yeah, and it
yeah,
raises the question, how well do you need to know spectral indices? When you do the catwise versus NVSS, you're making very different corrections for one of those factors.
yeah.
So, yeah, understanding that would be useful.
Absolutely. I show it here? I did. So the spectral index and X do actually have a significant effect because what happens is even with a particular velocity that you're inferring, you're going to get, let's say we're moving at a particular velocity, you're going to get a different dipole amplitude in all these surveys because they all have slightly different X, which is your relation here in log space, and different alpha. From the work I've done, I find that your choice of X and alpha is important because it will also change the velocity that you expect because that X and alpha essentially scale the amplitude with the velocity. So it is important there.
Thank you.
No worries.
I think
Nick, I'm just looking at the order on my screen.
Nick, did you have a question?
I might ask Nico.
Hey, I completely agree with Larry. Excellent talk. I have a quick question on maybe slide number 10, where you show tensions between Planck and different.
Yeah,
Right. So the catwise and the NVC and NVSS, they are sort of consistent, right? But the discrepancy between NVSS and Planck is 2 sigma, but it's 5 sigma between catwise and Planck.
yeah,
So how is it the
yeah. Yeah,
number of
how can
forces?
these have different relations if these are in so close? What it is that in I should have had a figure ready. In the posterior space, like of a corner plot, for example, MVSS and catwise are pretty much right on top of each other. which is really strong and interesting. So that's why they're in such low tension. But Catwise, because it has about 1.6 million sources, is a really tight, small posterior. So in terms of how many contours it is away from Planck, it's a lot. So it's in high tension. Whereas whilst MVSS is centered at the same location as Catwise, so they're in not much tension, MVSS has many less sources. The samples they're using is around 350,000 with a 15 millijansky cut and I'm asking. So which means the MVSS posteriors are much less constrained and they're wider. And that's why they're in less tension with Planck, even though MVSS and Catwise are in agreement.
All right, so that's the number of sources. Okay.
Yeah. And that's why I talked a lot about how more sources are coming out and RAX is exciting and EMU and SKA because MVSS is probably one of the most well understood radio surveys. We've had it for 20 years, but we just need more information.
Right. So more number of sources in racks, there is better consistency in the discrepancy.
Yeah. And if you want, if we have the time, I can quickly get up those corner plots. I have them on another slide deck if we want.
No worries. Thanks.
Okay.
Nick, did you want to try again?
Yeah, Nick?
Can you hear me now?
Yes.
Okay, excellent. Yeah, lovely talk. I've been thinking about this topic ever since I read the Blake and Wall paper.
Over 2002.
Now, yes. Yes, I was just kind of wondering, has this tension led anyone to really try and look at solutions to general relativity, which kind of weaken which aren't based on a strict assumption of homogeneity?
Yeah, so
obviously there's large scale structure. We know that, and so at some point it's not quite true. Yeah. Sorry, I interrupted you.
No. Absolutely. So I have a slide here for this. This one. So yeah, we're starting to question why we need homogeneity and isotropy. And there are certain solutions that have been proposed. Whilst this isn't exactly what I'm looking at after my own research, I do understand it a bit. So it has been proposed that an inhomogeneous cosmology could be a solution, meaning that we have a much large scale structure than we think, and we could be in a dark matter supervoid of the order of 1 to 3.4 gigaparsecs. And by being a couple hundred megaparsecs off the center of that void, that would be disrupting the way in which we're viewing the cosmos around us. And that could then account for the anomaly of the cosmic dipole. It has been proposed, whilst quite an extreme solution. And the other idea is the cosmological principle assumes this symmetry in the universe and symmetric expansion. And to solve the dipole problem, you'd have to break that symmetry. And in terms of how you break it, that's not something I can answer because you could break symmetry infinitely many ways. And you could have a tilted cosmology or essentially anything that isn't Friedman. So that would also be a solution. Or it could be something entirely new. Also, part of your question was if anyone is looking into this. I believe people are, but I'm not as familiar with their specific work regarding solutions to the cosmic dipole in terms of changing cosmology. Essentially, we're still trying to quantify whether cosmology has to change, because whilst the Catwise result is a 5 sigma tension, we need to understand exactly what's going on with the Catwise data. And also, we want to see the same level of tension with the radio if it is real. Because if radio is still not in high tension, then maybe there's not a problem. So we're still trying to work out exactly what has to change.
Thanks.
All right.
Thanks. Hi, Molly. Yeah, that was a great talk. I was wondering to what extent you're in touch with the EMU cosmology team. If you're not, that's not a problem. It's good to have competing teams working on the same problem. But there's been a lot of thoughts given in the EMU cosmology team to the various systematic effects. So you might actually find it useful. I mean, I guess if you're a member of it, I don't know whether or not you're a member of EMU. If you are, then I guess you should be in touch with them. But are you?
Yeah, so in answer to your question, I'm not personally in touch with the EMU team. Tessa sent me the email after Grant put my name forward for the talk as the first correspondence I've had with EMU. But I understand Grant is part of the cosmology team. So because we're his PhD students, in a sense, we are part. But officially, I just sent an email at the start of this meeting to the EMU manager to get added to the mailing list and added to the team. Okay. And it's useful to know that you have people already working, thinking about the exact systematics in regards to EMU.
Yeah. So there's
in regards.
Sorry, just to say there's a Zoom meeting every
typically every couple of weeks or so.
Oh, that'd be great. Yeah.
Which you should absolutely join, because you get a lot of discussion of things like this.
So our master plan, our wish for the future, is that we can take, because essentially any survey of objects that are all the same and we think are cosmologically distant can be used for this test. And in an ideal world, our dream is to have all these surveys in this interconnected grid, looking at the tension, what's going on between all of them. And I wanted to do that for the first couple of papers, but I realized I need to do it systematically and slow. So what I want to do is go through all these surveys, and I have a huge list of them. And EMU is very close to the top of the list because it is exciting. So I've been wanting to get around to EMU for quite a long time now. And I'll talk about one more thing, which is the systematics and looking into that. I've mainly been doing that for RACs lately, and I'm in the CSR Space and Astronomy student program, so I work with Emil Lenk and Stefan as well. And myself and Oliver, one of my colleagues, we're looking into this, not the systematics of RACs to say, but like what's going on in the surveys and how we can better quantify that and understand that. And I'm not too much over the similarities between EMU and RACs, but I know there are some there, so that can probably relate to. Yeah.
Great. I wish you every success.
Thank you.
Thanks. Any final question? All right. Thanks
Thank
again,
you.
Molly. That was great.